Welcome to the Fundamentals of Aerodynamics Project 2 overview for Xfoil. This is a three-part project where we'll be comparing three different airfoils and looking at their coefficient of lift, drag, and aerodynamic performance, as well as comparing one airfoil in three different flow regimes in viscid, laminar, and turbulent. And for the final part of the project, we'll be adding flaps to one of the airfoils at multitudes of degrees to see their different characteristics. We'll start off in Xfoil. The procedure is about to be the same for almost all the airfoils, and we'll launch Xfoil now. Okay, we're going to launch Xfoil. Just make sure it's all in one folder, and we're greeted with this black screen with white text. We're going to start off with the first airfoil. We have three airfoils. It's going to be NACA 0015, which is a symmetric airfoil, NACA 2415, which is cambered, and then we're going to end off with the Clark W airfoil, which is another cambered type. It's a specialty airfoil that we're going to have to get from a different database. We'll start off with the NACA 0015. We can simply type that into Xfoil to get its properties. For all the airfoils, we're going to have to hit pane to smooth it out, as well as PPAR to start defining the different parameters that we want. We would like to have a bit more of a mesh here, so what we're going to do is change the number of panel nodes by hitting N, and I'm going to change it to 250 for every airfoil that we have. And our trailing and leading edge panel density ratio, we're just going to keep that at 1. So if we hit T1, that will change that as well. If we hit enter, we will see that our parameters have changed here. What will be next is we're going to get into the actual operations of finding the different coefficients. We can hit enter to get out of the PPAR menu, and it brings us back to the Xfoil menu. From here, we can type OPER for operations. In this model, we're going to change it to viscous, V-I-S-C, and we can see that it'll ask us for a Reynolds number. In the project, we're assigned 1 million to be our Reynolds number, so we'll go ahead and hit 1 million, that's 6 zeros, and we'll type that in, and it'll set that. We'll do 100 iterations. It should be fine with that, so we'll type iter, hit 100, and we should be good to go. Now, we want to change and check a range of -5 to 15 degrees of angle of attack. To check that, we can do ASEQ. It's alpha sequence. We can start with our first angle, which is -5. We can go to 15, and then we will iterate by one angle each. If we type that in, we can see that it will give us our lift coefficient, drag coefficient, and its corresponding alpha for this symmetric airfoil. Obviously, we have the name up there, NACA 0015. To save this to a file, we can hit PACC, and we can see that the polar save file name has come up. We'll just save this as NACA 0015, and don't worry about the dump folder. And now we can be in accumulation mode. Once we're in accumulation mode, we can run the same test, which will be our A sequence, -5 to 15, iterating over 1. And we can let that run, and that'll bring us to our text file. If we navigate back to our file that we have our Xfoil saved in, we can see that a file was made. We can look into that. We'll check it on Notepad first, and we can see that our results were just tabulated within Notepad. Later we can export this to Excel so we can compare all of our airfoils. This is going to be the same process for all of our airfoils. We will change a couple things up with the Clark since we will be importing it since it's not inherent to Xfoil's programming. And I'll show you that. I'll also show you the export into Excel to get forward with that. From now on, I'll just speed up. I'll show you the NACA 2415, and then I'll slow down to show the Clark KW, or the Clark W import process as well. So I'll see you in a bit. So we loaded our solution for our NACA 2415. Like I said, it's a repetitive process for all the airfoils. We set our PPAR parameters when we did the geometry of the airfoil, and we set our iterations just like last time, and we come out with this tabulated result that we can eventually export into Excel. We're going to move on to the Clark W airfoil, which is going to need a slightly different process. In order to analyze the last airfoil for part 1 of the project, it is the Clark W airfoil. We cannot use Xfoil explicitly because they do not have an internal diagram for the Clark W airfoil. We'll have to navigate over to the UIUC Applied Aerodynamics Group database. They have a variety of airfoils that have different points and coordinates that we can take and import into Xfoil. To get to Clark, we'll just navigate to the C alphabetically, and we can see that Clark W, the data file, as well as the GIF file, so we can get an image for it. With their data file, they order their points. Their top surface is from leading to trailing, as well as their bottom surface. This is not going to be compatible with Xfoil, and we'll have to manually flip this around. Xfoil wants a order of trailing edge to leading edge, and then leading edge to trailing edge, basically going counterclockwise around the airfoil. We'll throw this in a text file and manually change it, and I'll show you what that looks like before we import. So we can now see what I did here. I switched or flipped these values, starting with the 1 and navigating downward. That's starting with the trailing edge first. Then we go all the way to the leading edge, where we omitted the second 0 point here. We don't need 2 of those, that will confuse Xfoil. And then we kept going on the same way with how they have it. This is the format that Xfoil will need: trailing edge, leading edge to trailing edge, going counterclockwise over the top surface to the bottom surface. So we can load this into Xfoil. We'll close out of this by typing in the command load, and we need to enter our file name, which it's called Clark W, and we have to keep in mind that it's a text file. Since it is that, we do Clark W, and then for the text file we do .txt, and we can see that the airfoil matches up with what we find here. So if we get back into Xfoil, we can continue with the same parameters that we did before, and I'll speed through this since we've already seen this before. Okay, we can see that we got the Clark airfoil in this tabulated notepad. We can see that it left out one of the degrees. We'll have to just rerun that. Sometimes it doesn't converge correctly. It's a bit of a process with Xfoil sometimes to get things to converge correct. But we'll get that fixed up, and I'll show you how to tabulate this into Excel so we can start our first part in graphing all the lift, drag, and aerodynamic performance coefficients. All right, we have tabulated all of our results for that first run into Excel. We can see that the data files just transferred over pretty well. and we tabulated it to compare the different lift coefficients, drag coefficients, and aerodynamic performance for each airfoil. What we can see here is as we camber the airfoil more, we move our angle of attack of no lift further back. So we have a negative angle attack to achieve no lift, or in this case, if you look on the vertical axis, we have some lift at zero angle attack with the cambered airfoil. If we zoom in, we can analyze it for thin airfoil theory. I went from the -5 to +5 degrees, and we can see that our slopes of these lines, this is just a zoomed in version of this, is around 0.11, which is in line with thin airfoil theories. We have 0.11 per degrees as our slope for thin airfoil theory. Similarly, with the drag, we can see that our more cambered airfoil receives a little bit more drag as we go along, but they all stay within a similar regime here. And then finally, our coefficient of error performance. We can see that we max out a little further back from each other. So the green values are our maximums, red is minimum, and green is max. And when we're looking at the main results, we can see that as we increase the camber of the airfoil, that our corresponding alpha will be moving slightly back, as well as our minimum drag coefficient and lift coefficient that we talked about earlier. So we'll be doing something similar in the next part. We'll be doing a comparison of different flow regimes, again, in viscid, laminar, and turbulent. The only thing we have to change when comparing the airfoil is changing that the Reynolds number value in Xfoil. You can see that earlier in the early tutorial we made that 1 million for the Reynolds number. And we're going to be only comparing the Clark airfoil for the next example. We already have a run here, but I'll show you how to get that done. So we'll run through that quickly and come back to a results page similar to this, but you'll see everything in a time-lapse mode. A little note here, when we first do the opper, we didn't set it to visc, which it says opper I. This is how we'll be doing the visc or the inviscid case for the Clark W airfoil. For the other ones, we'll be doing a Reynolds number of 300,000 for our laminar flow and another 1 million, which will be exactly the same as our last run in the Clark for our turbulent. We'll get back to it. We have tabulated all those results that we just typed in for all three flow cases. We can see those here. One thing that I forgot to mention prior is when we're calculating our aerodynamic performance, that we did that in Excel. So we just did a simple division of the coefficient of lift divided by the coefficient of drag, but we did that automatically in Excel instead of in Xfoil. So into part 2, we can see that our coefficient of lift, our inviscid flow, or our ideal case, just keeps a constant slope here with no drop off because we don't see any flow separation. And then laminar, we have a bit less lift in this case, and then turbulent, we have a little bit more. When we go back down to the drag, we can see that drag has become more of an issue for the laminar case. With the more energized flow, turbulent remains in the middle, and then in viscid, we don't have any drag condition. Since we don't have a drag condition, we obviously can't calculate the aero performance of the inviscid, so it's just dividing by 0, so we had to omit that from this graph. But the other ones, we can see that the turbulent has a higher aero performance versus the laminar, and they just about happen at the same point in time. 4 degrees, 5 degrees. I guarantee if we iterated a little bit more in between that, it would be a little bit closer. But they're pretty on par with each other in their maximums. If we want to see our main results, we can see these tabulated here. Obviously in viscid flow with our lift coefficient max and at what degree it happens. Similarly, the minimum drag coefficient and where it happens, and the max error performance. We're going to go into the last part of this project. That will be comparing different flap angles for this airfoil. We're still going to be using the same airfoil, the Clark W, and I will show you how to insert flaps once we're into that part. The first part is going to be identically to the turbulent flow, as well as to the last part of Clark W, because we're going to be running this simulation at 1,000 as our Reynolds number only. But we'll jump into that soon. Okay, we are in the part 3 for this project. We are going to be adding flaps. We've set up the airfoil like we did previously. This is the Clark W airfoil, and we have the panel nodes of 250 and the trailing leading edge panel density ratio of 1. Make sure we're in the Xfoil menu, not in the parameter changing menu up here. We're going to hit GDES for geodesic. It's going to bring us to a new menu where we can see our airfoil. And then we're going to type flap to add a flap. We're going to choose our hinge location. For this project, we're going to use 0.7 from the chord length, so about here. Get back into Xfoil. And we're going to enter the Y location. We're just going to hit a 999 so we can specify where we want that in respect to the thickness of the airfoil. So we're going to just put that in the midpoint, so 0.5. So it's going to be half the thickness of that area, or of that height in the 7th region. We'll go ahead and hit yes for that. And in the project, we want to test 0 flaps, which would not be useful here in this case because we already have that calculated out from the previous runs. And we need to do 10 degrees down and 20 degrees down. So we'll start with 10 and keep in mind that a deflection of a positive number is downward. So we'll see that hinging down. Now to save these new parameters, we're going to hit exec, EXEC, and now we can see that it made us a new airfoil with new nodes, and we can hit enter to exit out of this. Now we can go back into our PPAR menu, and we can see that we have to repanel this airfoil since it changed geometry. So we're going to do the same thing again, just setting our panels to 250 and that ratio to 1. We're going to continue just like anything else and run the simulation, and you'll see that soon. Okay, I hope you liked seeing the calculations going on there. We did have a slight issue on the last flap, the 20 degrees, with the geometry that we were using. Finally, we had a little convergence issue for the -2 and 1 degree angle of attack. So we cannot get those values, but everything else worked fine with the 10-degree flap and obviously the 0-degree flap that we've seen before. Into the results, we can see that that's omitted the no convergence areas, but we still get a good picture of what's going on here. So when we're comparing our coefficient of lift, we can see that with no flaps, we just keep our general curve that we've seen before. And as we increase our degrees of flap, we inherently get higher lift coefficients. So that's the 10 degree and going up to the 20. Now, on the downside of having flaps, we also increase our drag. So with our coefficient of drag, as our flaps go up, ultimately, our drag goes up. And the coefficient of aero performance, we can see it's kind of all over the place here. We've seen this graph before, and it's interesting to me that the flaps at 10 degrees starts maxing out around 0, and we probably would see a max around 0, maybe -1 if that point wasn't omitted for the last seeing this the gray trend here. But definitely an interesting aero performance angle of attack. Obviously, if you're increasing the angle of attack with flaps, you're even increasing more drag and more lift in some cases. So we'll go into our last results page. This is similar to our part 2 results page. We can see here that our CL max, that's corresponding with our angle of attack. We can say we're relatively in the same angle of attack, but obviously our CL max is going to be higher with the higher number of downward flaps. Similarly, the drag, we increase that like we said earlier, and then the angle of attack that those occur at. And then ultimately our max aero performance that we see here. So that would be everything covered for project 2. That is the third part that we just finished up here. We compared the differences of flap angles on the Clark airfoil. We compared the difference of flow regimes on the Clark airfoil. And then we compared the coefficient of lift, drag, and aero performance for 3 different airfoils of differing cambers, symmetric, a cambered NACA 2415, and the Clark, which is slightly more cambered than the NACA 2415. So that's going to be everything for this tutorial.